What I want to do in this video is make a clarification of Fatou's lemma that I probably honestly haven't really given much thought to. And I don't think most analysts would really give much thought to it, just because it's sort of like I wouldn't say a trivial clarification of Fatou's lemma, but I guess our brains are so wired doing analysis research that kind of is like, well, yeah, obviously, but you know, but still, it's worth clarifying. Um, okay, yeah, so in the video consequences of Fatou's lemma, I mentioned that what the book calls the generalization of Fatou's lemma is really the Fatou's lemma that more or less most people call Fatou's lemma. Okay. And yeah, this is the screenshot that I have from that video. Okay. But for applications, particularly one of the prelim problems, and I want to go over that after I do this, um, and give you kind of probably the most streamlined way to do that, the prelim problem, the generalized Lebesgue dominated convergence theorem, the proof of that rather. So yeah, when you actually apply Fatou's lemma, you really want to use something that's a lot more general in the following sense. And it's something that, yeah, us analysts would just kind of we just wouldn't think. I mean, we just would just use without giving it much thought because we're so wired into thinking, well, excising sets of measures zero is so trivial, it's not even worth calling it a new generalized Fatou's lemma. So let me share the board before I say anything else. The hell did the board go? Um, okay, this is strange. Yeah. Okay. Sorry about that. Okay. Yeah. So if kind of excising sets of measures zero is not yet branded into your brain as kind of a trivial matter, then this is what I would remember as Fatou's lemma. Right? So it's almost what I had a second ago. If each Fn, so this definitely could be a generalized real valued function. So it could spit out plus or minus infinity. So we want these to be measurable and non-negative. So it could possibly spit out plus infinity when I say non-negative. But the key is the best we can really, well, we need this flexibility. Uh, yeah, we need this flexibility to do the prelim problem, essentially, in an efficient manner, rather than just use what I had up a moment ago as Fatou's lemma and then kind of have to repeat excising sets of measure zero. It's just not efficient. All right. Uh, yeah, so if this is true, then the conclusion of Fatou's lemma, what the book calls again, the generalized Fatou's lemma, which no one else calls it that. Very strange that they and even in the updated version they didn't kind of change that. Yeah, I have never seen anyone else literally in all the history of analysis call call something like this the generalized Fatou's lemma. Okay. Yeah, so the proof is pretty trivial given what I had on screen moments ago. So in other words, uh, given this, the proof is basically almost trivial. But I'll repeat it as a kind of you know, an example of excising sets of measure zero that are strewn throughout the videos. Um, all right, so let's say Bn is the bad set. So what's bad? Well, it's bad uh, if Fn of x is not non-negative. All right, so this is measurable, and in particular, um, well, we're assuming each is non-negative almost everywhere. So the set where it's not spitting out 0 to infinity, including possibly infinity, has measure 0. That's the definition of almost everywhere. Right. So that means the union of these sets, which I'll call B for bad, has measure 0. All right. So this, well, just repeating what I have here, has measure 0. Okay, so first of all, what is this? Yeah, and we've done this probably, it's probably in the videos a dozen times, but again, I'll just review this kind of whole thing here. So B is this union, and we're taking away a union, so it gets converted into by, I think it's De Morgan's law. E take away Bn. So X is in this set here. Okay. So we're away from each Bn. If we're away from each Bn, then each Fn of X is in 0 to infinity. All right, so I'll just write that down. Okay. We're away from each Bn, so this is in 0 to infinity. For every natural number, little n in natural numbers. So a little redundant there. Um, right. Okay. So yeah, now we're basically done. So kind of so each one of these is measurable because B is measurable and Fn is originally measurable. So no issue with measurability. All right, so now I can apply the original Fatou's lemma to Fn restricted um, to E take away B. So technically, I really mean Fn restricted to E take away B, but whatever. That's kind of splitting hairs here. All right, so yeah, I am applying uh same thing. This generalized Fatou's lemma, not to Fn, but to Fn on, sorry, not to Fn on E, but to Fn on E take away B. Because each Fn on E take away B is non-negative. All right. And so we're basically done because well, we're excising a set of measure 0 that has no effect on integration. Um, yeah, B has measure zero, so I can excise um I can excise this set of measure zero, and it's not going to affect anything whatsoever. All right. So these are non-negative. All right. Yeah, and so a bit of a clarification. This integral here is fine. It's well defined because each fn is um non-negative almost everywhere. So the lim inf itself is a non-negative function almost everywhere. It's in particular, this is non-negative, or rather, I mean, it could be infinity. Yeah, and for the purposes of integration, so this is, yeah, it's, you know, we don't care what it does on B. We can even set it to be zero on B for all we care about. Sorry, my dog is giving me a little bit of a little bit of a headache here. Hey, come on, buddy. Say hey. Want to say hi at the camera? No. All right. Anyway, um, right. So, yeah, and so hey. Sorry about that. Yeah. Okay. So, now she's nice and calm, just kind of hanging out here. I can't really see her too well, but yeah, she's just okay. So yeah, now I can use Fatou's lemma, what I just had up for. So this is less than or equal to the lim inf. And certainly yeah, so this certainly exists because these are non-negative, each one of these. Uh, and again, excise the set of measure zero again, or because B has measure zero, this equals. And again, for clarification, each Fn is non-negative almost everywhere. So, you know, this integral is fine. We don't care even how you redefine it on uh that you know on E take away B. It just doesn't matter because the set of measure zero. Fn is non-negative almost everywhere. So this integral, and it's measurable, so this integral makes sense. Okay, so yeah, so let's see how this little, by analysis standards, kind of almost trivial generalization of Fatou's lemma. Let's see how this makes this problem, the prelim problem, the generalized Lebesgue dominant convergence theorem, just that much easier. So this helps. Right. So this is the problem. Number three here. So yeah, it's the heart of the matter is similar to the proof of the Lebesgue dominant convergence theorem. It's just a lot more of a pain, just making sure everything is well defined. But um, right. So yeah, you can go back to it. This is what I'm going to prove using this generalized Lebesgue dominant convergence. Sorry, using this kind of generalization of Fatou's lemma that you probably should kind of brain into your brain. Um, Namely that you only need to assume these are non-negative almost everywhere. Right. Okay. So the proof of the generalized Lebesgue-Dominic convergence theorem, that prelim problem I just had up. All right, so same basic proof as I did as that example, as I did on the board like a week or so ago. I'm gonna do it maybe slightly different order, the different steps, but basically the same proof. Okay, so first of all, hell, this is gonna be a pain. So yeah, I'm not gonna do this because it's gonna be way too annoying. Um, Let me go to paint here. Fortunately, I think paint has turned itself into something very annoying. Uh, okay, not so bad. Okay, so yeah, now I can go back and forth here much more easily. All right, so I'm going to prove this. All right. So, yeah, so first of all, this is true. So you can say we can assume each GN is integrable, and that'll be fine. But to be careful here, if you really want to be careful, let's pick N. 1 second. This thicker. That's much better. So use definition of convergence, N bigger than big N, applies anything, literally anything works here. Let's do 1. So in other words, that means as long as little n is bigger than big N, then well, so I'll do it like this. There's always less than or equal to its absolute value. Less than 1. So that implies if n is bigger than big N, in particular, this is finite. Right. Okay, so this is quite useful. That implies because each GN is non-negative and integrable, that means this is finite almost everywhere. All right. And says the same thing about f of x. Because the problem assumes this is true. This is true almost everywhere on E. So two things are true almost everywhere, then, or if property A is true almost everywhere, property B is true almost everywhere, then property A and property B are true almost everywhere, just because the union of two sets of measure 0 has measure 0. So this is less than or equal to Gn of x is less than infinity. That is true for almost every x in E. Right. So yeah, this is I would definitely say this is a tricky prelim problem. This is one of on the medium to harder side of things. Um, yeah, so what does that mean? That means, well, just kind of repeating what I have here, and in particular, uh, so this is uh yeah, so this is going to be less than or equal to, I'll do it here. So this is true almost everywhere. And in particular, the one of the point here is this has meaning. In particular, it's not or rather, let me do this. Both of these are non-negative real numbers almost everywhere on E. So it makes sense to subtract it. We're not doing infinity minus infinity. That we're not doing any infinity minus infinity stuff. So everything has meaning here for almost every x in E. That kind of got cut off a bit. Second. Okay, and to be clear, this is just kind of the trivial property of or here I'm using the trivial property of absolute values that plus or minus f of x, fn of x is less than or equal to absolute value of fn of x. I mean, they could be equal, but it's always less than or equal to. Um, so, right, so minus absolute value of fn of x is always less than or equal to plus or minus fn of x. Technically minus plus, but it's the same thing. So yeah, minus makes it go the other way. All right, so let's define, and I don't know how useful it is to do this, but big F plus or minus n of x to be um, yeah, so the point here, so let me not even say on E. So forget I said that. So the point here, and I really don't want to harp on this too much, and we don't really want you to harp on it too much on the prelim either. Um, just we just want to see that you're aware of this kind of phenomenon here. Uh, so technically, yeah, this is not defined on E, on all of E, because you could have infinity minus infinity going on, but at least for almost every x in E, I'll do it exactly as I did before. For almost every x in E, this makes sense. because of this here, and it's non-negative. All right, so yeah, I have a very useful and certainly measurable because it's the addition or subtraction of measurable functions. Okay. So yeah, we can use Fatou's lemma, all right? Because we have, and you can read the, and if you're saying, well, what about well, on this bad set of measure zero where it's not defined to be zero. I don't care. No one cares what it's defined as to be on a set of measure zero because it's irrelevant for integration purposes, right? Yes, when you get into much more advanced analysis like partial differential equations, there, you want maybe functions to be continuous or differentiable. So then, yes, it matters, but we're just doing integration here. So on this bad set, the set where this maybe is not true, and this got cut off. Oh, sorry. I see why, because I accidentally cut it off. Yeah, so you can redefine it however you want on the set where this is all not true. If anything, just set it to be zero. You could set it to be plus infinity. You could set it to be zero. You set it to be minus infinity. Does not matter one bit. And you don't really have to explicitly say what it is. Just leave it as this. This is true for almost every x. So I can use the Fatou's lemma I had a second ago. Um, and it's also measurable on E. Again, redefining it however you want it to redefine it as on this bad set of measure zero where this is not true. And this doesn't even make sense. Okay, so let's apply Fatou's lemma. All right, so what's Fatou's lemma? And we'll see what the left-hand side and what the right-hand side each are. So this is Fatou's lemma. Um, so let's do the left-hand side first. All right, so yeah, and I think when I started this problem off with this, what I'm doing now, um, on the board, which I didn't really use it until this point, so I'm not sure it was very smart, but okay, so by again Fatou's lemma, well, so this is kind of one of the consequences of Fatou's lemma. If you forget it, I'm just gonna say it's Fatou's lemma. So this equals because Fn converges to F almost everywhere. So then particularly absolute values converge almost everywhere and are non-negative. Whoops. I mean, really, you could just say by Fatou's. You don't have to go through all these steps. Let me explain that in a second. So yeah, Fn an absolute value converges to F almost everywhere. So this is true. And this is Fatou's lemma. And this is finite. Well, let me not skip steps here. All right, so almost everywhere this is true. So, right, this is less than or equal to this here. The assumption is that the limits are equal here. Sorry, there's no need for absolute values because each gn is non-negative. And G is integrable. So the whole conclusion here, really, if you even just want to say by Fatou's lemma and the fact that these two things here, you could really just say by Fatou's lemma, and because these two things are true, then F is integrable. You write that, we're going to be fine. But I guess when in doubt, put more detail. But yeah, the whole point here is uh, purple. This is integrable. That's what we really want. Uh, so in particular, F is integrable. And so this is also finite. Well, G is integrable because, well, problem's telling you G is integrable right here. So also G. All right, so where is this going? Question. All right, so the conclusion is that this is going to be equal to Gn plus or minus Fn of x. I can make that a little neater. Right. Right. And so remember, for almost every x, this makes sense. In particular, yeah, for almost every x, no, this is non-negative, in fact. So in particular, makes sense. Right. Gn goes to G almost everywhere. That's the problem, part of the problem. Gn goes to G almost everywhere. Fn goes to F almost everywhere. That's what's here. So almost everywhere, this equals G plus or minus F. Sorry. Right. Um, I mean, so each one of these is non-negative. Almost everywhere on X. And so in particular, this is going to be non-negative almost everywhere on X. But both of these, I want to emphasize, are real valued because they're both finite almost everywhere. So in particular, this is non-negative almost everywhere, and um, both of these make sense. They're real valued, so there's no issue whatsoever. Both of them are integrable, real valued. Um, this makes perfect sense. There's no ambiguity issues whatsoever. Anything I'm doing here, almost every. I suppose technically you should keep excising sets of measure zero and build a new, bigger set of measure zero. Don't bother for the prelim. If you give me detail at this level, I'm very, very, very happy. Seriously. Um, okay. So that takes care of that. Now let's do the uh right hand side. So it's a little easier. So maybe let's actually get what the left hand side is. So it's this lemma. So this equals almost everywhere g of x plus or minus f of x. Both are integrable. And so this is going to be equal to maybe just do it like this. Really don't want to write of x's everywhere. Annoying. Yeah, both are integrable. So this is a well-defined real number. The integrals make sense. No problem whatsoever. Okay. Takes care of the left-hand side. And let's take care of the right-hand side, which is a little simpler. I mean, even if you forgot about all these technicalities of stuff being well defined, um, you'd probably more or less consider it correct. Um, you know, so but anyway, okay, so this one is yeah, a little quicker. So this equals uh mm gn plus or minus fn. Okay. Um each gn and fn are integrable, at least for large n. Going back up here. Um and little n bigger than big N means integral of gn is finite, and same thing is true for f, and because, well, fn of x is less than or equal to gn of x, an absolute value, fn of x rather, for almost every x. So again, both are integrable for large n. Taking limits, still n goes to infinity. So the problem. So I can separate the integrals up. And the assumption is that Gn, integral of Gn goes to the integral of G. So we can use that to say this is integral G. Um, yeah, so it's going to be plus the lim inf. So we can kind of think of this as like integral Gn plus this here. So that's why I'm doing it like this. Um, right. All right, so I'll put this in brown also, I suppose. Particularly, this is equal to the following. All right, so now we are almost done. All right, so plus, all right, so this is the left-hand side. And remember, the left-hand side is less than or equal to the right-hand side. Plus here, this is half of what we want. And remember, the FNs are not necessarily non-negative, so you cannot just use Fatou's lemma to get the half that you want. You can only do that for the monotone convergence theorem for that proof because there you're assuming the FNs are non-negative. Okay. All right, so cancel out integral of G's because they're finite by assumption. Yeah, so this is half of what I want. And minus that little magic trick of lim inf of something minus equals minus the lim sup. Right, so again, left-hand side is this here. So it's integral G minus integral F. And that's less than or equal to a minus here. I was going to get that to look decent, but it's decent enough. So this is integral G minus lim sup. Okay. So again, cancel the integrals here and just minus everything. That's the easiest thing to do. So you minus everything, the integrals get, the inequalities get switched. And so we are done. So it's integral, um, this, or rather bring this to the add this to both sides, add this to both sides. This is less than or equal to the integral f. So we have this is true, and we have this is true. So these two combined, limb sup of the integral of fn is less than or equal to the integral of f is less than or equal to the limb inf of the integral of fn. That's equivalent to uh, so what I mean is the two things in yellow combines uh, to give this limit Fn equals F. Right. Yeah, again, this is to do this carefully is a pain. Okay, I wouldn't say it's hard. I would say it's a pain in the ass, bluntly. So, but yeah. All right. Well, any questions on this, let me know. Hopefully this helped. So long, take care. Bye-bye.